Welcome everyone. Thank you for joining the RISE EC Computer Engineering Distinguished Speaker webinar. So before introducing our speaker today, let me briefly go through some logistics. So first, if you have questions during the talk, you can message me in the Q&A chat. At the end of the talk, we will select those questions to be answered by our speaker. At the same time, I will also monitor the Q&A chat during the talk. In case there are questions that it makes more sense to clarify in the middle of the talk, then I will unmute you and let you speak your question. And then second, this talk will be recorded and uploaded to our department's YouTube channel for future access. Next, it's my great pleasure to introduce today's distinguished speaker, Dr. Kailash Gopalakrishnan, who received his PhD in electrical engineering from Stanford. After that, he joined IBM, where he is currently an IBM fellow and a senior manager of the Accelerator Architectures and Machine Learning Group at IBM T.J. Watson Research Center. He has worked in the area of computer architecture, deep learning, semiconductor device, circuit design, and emerging memory devices. He and his team have primarily contributed to the invention and development of specialized platforms of deep learning that have significantly improved industry-wide AI system performance, and also revolutionize the incorporation of AI capability within IBM system. In particular, he and his team have made pioneering contributions to the field of precision scaling for efficient deep learning inference and training. For example, they published the very first fixed point deep learning paper at ICML back in 2015, which already gained over 1,000 citations. So today we are fortunate to hear more details and also his unique insight during the talk. So now I'm going to pass it to Dr. Gopalakrishnan. Hi, Kailash, thanks again for accepting our invitation, and the rest is all yours.
Sounds good. Thank you very much. Let me share my screen, and maybe somebody can tell me whether you're able to see my screen.
Yes, I can see.
Okay, very good. Thank you, Celine, for the generous introduction. And thanks very much, Aki, for organizing this talk. I'm deeply excited to be here, to be speaking to all of you. Just a brief introduction into myself beyond what Celine said. In my current role, I manage all of the CMOS compatible AI hardware activities within IBM Research, including algorithms, digital hardware design, verification, software development, and as well as interface with all of the key business units within IBM. What I wanted to talk about today is to walk you through my perspective on what the future of AI looks and how it's shaping computational requirements, right? And a key feature of this roadmap that we've put together in collaboration with researchers across IBM and outside, as well as collaborators in various universities, including Celine, is this enablement roadmap that focuses on bit precision scaling that I'll share with you, and I'll share with you why it's so exciting and why I believe it's critical towards supporting higher and higher compute requirements for deep learning. So with that, let me go to the next chart. I wanted to start by introducing deep learning compute challenges, I think, in the first few charts. And most of you know a lot about this, so I'm not going to spend a lot of time on it. But I'll first then introduce the precision scaling roadmap that is so critical to meeting these compute challenges. After that point, I'll describe a little bit about some of the key innovations that can enable highly scaled precision for inference, which specifically focused on less than 4 bits of for inference. After that point, I'll turn my attention to training and focus on how recent innovations have enabled ultra low precision, specifically 8 bits and lower for training systems. So I'll give you an overview of some of the recent published work on that space, as well as focus on what it takes to go beyond compute and specifically compression of gradients and so on and so forth for training systems. I'll also give you a brief introduction into some of the hardware activity happening inside my teams and specifically in IBM Research and IBM Systems. I'll finally then conclude my talk. I just wanted to warn you that I have lots of slides and probably I want to keep the talk to under 40, 45 minutes. So I might go a little faster than I would like, but please do stop me at any point if things are becoming completely murky. So with that in mind, let me jump right into it. Most of you are very familiar with some of the computational requirements of deep learning training and inference. And this chart kind of puts all of that together and describes some of the key bottlenecks and some of the key areas where we need a lot of computational help today. One of the key areas where is obviously focused on model training. This is something I'm sure many of you know a lot about. And I think the key challenge here, obviously, is that it still takes days to train really large deep learning models, and sometimes even weeks, on GPUs. So you have to build large GPU clusters, and essentially you need to make sure that you can get the sufficient compute so that you can train these models repeatedly or quickly. This has been what has driven GPU development and sales for the past many years. But over the past couple of years, we are seeing that inference is becoming really important. And obviously, because typically, once you build a model, the amount of ops you need to train the model total, you typically spend somewhere between 10 to 20 times to do inference. So inference obviously is becoming an increasingly important workload. Currently, all of inference is run on CPUs, but it's transitioning to PCIe attached accelerators as well. And one of the critical trends that I want to bring up here is the fact that AI is being infused across a whole bunch of applications. So things like transactional workloads, databases, MongoDB, things like that. AI is being infused into it. And so you can imagine that as more and more applications get infused with AI, inference requirements will continue to grow in the data center. One of the applications that's really critical for us at IBM is transactional inference. IBM runs all of the servers and mainframe machines that power all the banks and the financial institutions and credit cards today. So a lot of the deep learning specific requirements for IBM focuses on transactional inference. You swipe your credit card, and by the time it gets approved, they want to do some form of AI and specifically deep learning to make sure that this is not a fraudulent transaction, as opposed to what we do today, which is after the transaction is granted, you typically, you mark whether the transaction is fraudulent or not. Lots of industry use cases here. It drives its own specific set of hardware. The fourth part here focuses on autonomous driving. I think, again, this is under the very latency sensitive application. Accuracy is really critical, so one has to be really careful about low precision arithmetic in this space. And finally, an emerging area that we see happening becoming quite important is basically inference on mobile and IoT devices, as well as federated learning at the edge. So you can imagine, because of privacy concerns and things like that, you don't want to send the data back to the data center. So how do you use a consolidated set of edge devices to do inference and do federated learning, right? And in some of those applications, especially things like security camera, maybe slightly lower accuracy is tolerable. So the main message in this chart is there are a bunch of different markets or verticals that are being created in terms of computational requirements for training and inference. Some of them are throughput centric, some of them are latency centric, some of them require inference, some of them require training and inference, and so on and so forth. And in all of these different sections, the computational requirements are growing very, very rapidly. So just to give you an example of some of that, I think on this chart, you see a couple of examples of deep learning training and deep learning inference. The left is focused on the training piece. And from our experience in IBM, we see that the compute time needed for deep learning training is doubling every 4 to 6 months. And this is driven largely by these really large models that we're seeing that are coming together for NLP. We need thousands of GPUs running for hours or weeks to train a single model. So this is a dramatic growth curve, as you can imagine. And this has huge implications on training cost and participation. If it takes $1 million to train a deep learning model, it's really hard to democratize AI. So it's really important to be able to reduce the cost and of both in terms of the time needed as well as in terms of the power dissipation, to be able to do that in a way that is consistent with building large models but is energy efficient. On the training side. On the inference side, we have a similar problem. So once you train a large model, you have to be able to deploy it. And these models are becoming increasingly huge. And so this is a plot showing various image processing models. And again, I'm sure many of you are familiar with this. But if you look even beyond image processing and look at NLP, the model complexity and the model size and the number of flops it needs is growing extremely rapidly. And so really inference is becoming a really important piece because you, in many cases, as the previous chart indicated, you have latency constraints and you need to maintain energy efficiency as well. So basically, both of these domains are exploding right now in terms of compute needs, compute requirements, and it's obviously caused a ripple effect in terms of the industry, in terms of what kinds of hardware are needed to support it. So to address some of these issues, well before the current AI revolution, back in 2013 and 2014, a team was put together at IBM Research, where we were looking to understand what are the computational flexibility associated with AI and deep learning, and what are the different knobs one can have to improve that computational efficiency. So this is essentially the field of approximate computing, right? And approximate computing is a broad concept. You can apply it purely in the software level, and people are doing that extensively today. You can apply it at the architecture or the chip level, and that's where precision and implementing low precision arithmetic onto chips comes into play. And then you can really go down all the way down to the device level or the circuits level. And that's where you can have essentially even more benefits in terms of energy efficiency. So if you look at the stack, going from the top to the bottom, the top ones are nearer term, the bottom ones are obviously much longer term. And essentially, all of these different factors can significantly improve the computational efficiency of AI workloads. And essentially, all of them take inspiration from the human brain, right? And so whether we talk about low precision arithmetic or we talk about stochasticity and we talk about various ways to introduce approximations. So basically, fundamentally, we have many, many knobs to apply approximate computing. And one of the things we concluded was the most efficient knob we can bring to bear in the medium term is the use of low precision arithmetic. And so my entire talk today will be focused on that piece and to try to give you a sense of all the work that has happened in this space. Now, the reason we think low precision arithmetic is so important is based on various hardware demonstrations that our teams have done, and both within IBM as well as folks across the industry. The advantage of using low precision arithmetic is that it has the ability to improve the energy efficiency at least quadratically, right? So this pictures the cartoonized version of what that looks like. So initially, when deep learning started, all of the inference and training were done on 32-bit arithmetic. So if you consider that to be 1x in terms of performance or energy efficiency or performance per watt, then as you reduce the precision, you are able to significantly improve the efficiency of the compute. The main reason that you can do that, especially if you are successfully able to go from 32 bits down to 4 bits and then eventually down to 1 bit, you can improve the precision, you can improve the energy efficiency by up to 1000x, right? And this comes about because when you design these circuits, when you build these MAC engines, deep learning is all about multiply accumulates. 99.9% of deep learning is multiply accumulates. So when you build these MAC engines, these multipliers and adders, the multipliers become quadratically more efficient as you reduce the precision, and accumulation there are lots of new ideas as well in terms of how one can improve the adder or the accumulation efficiency. So long story short, I think this is a really interesting direction where you can reduce the precision. If you're able to maintain model fidelity, then you can get significant gains in this space through improvements in energy efficiency and by increasing the throughput for a given power envelope. So we've, for our teams over the past 5 years, we have pursued this precision topic relentlessly, trying to drive down precision while maintaining AI model accuracy for both inference and for training. Okay. So let me try to give you a little bit of a flavor into some of the work that we did. So this is work that happened in 2014, where our team in IBM Research did the first piece of pioneering work that focused on doing deep learning training in low precision arithmetic. And so what you're seeing on this chart here is, if you ignore the roadmap that I'm showing you here, back in 2015, we were able to show for the very first time that we could use 16-bit arithmetic to do deep learning training without losing model accuracy. Initially, when we did that, we focused on fixed point quantization. Subsequently, we moved away from that work and we looked into floating point quantization. And on the right side, what you're looking at is back in 2014, the state-of-the-art models were the natural language classifiers, which were both CNN and RNN based. You had AlexNet, which was the state-of-the-art for image classification back in 2014. And of course, you had various models, DNNs, that were used for speech-to-text conversions. And what we showed is, as you can see from this chart, is that by correctly optimizing the arithmetic and understanding what are the sources of noise and sources of inaccuracy, you're able to maintain the precision across all of these domains. So we were successfully showed that 16-bit arithmetic could be used across speech, vision, and NLP back in 2014 and 2015. The ICML paper that published this work, which focused on fixed point quantization, was basically enabled using stochastic rounding. So one of the key ideas we had back then was, hey, we have to maintain bias in these systems, and we cannot add additional bias. And stochastic rounding really allows us to have an expected value of that bias being 0. So this really laid the foundation for 16-bit training in the industry. And the advantage, we also made a lot of hardware demonstrations, and we showed that we could get 16-bit arithmetic could be 4 to 8 times more efficient in comparison to 32-bit arithmetic. A significant improvement for deep learning training, which was obviously took a lot of time to train these models back then. So this was implemented both at IBM as well as in various industry products as well. It was implemented in NVIDIA Volta chips, Google TPUs, and Graph cores in the 2017 to 2019 timeframe. But this was kind of a first piece of work that we did that focused on, hey, we can use low precision arithmetic even for training, where it is really hard to maintain the fidelity of all of the different tensors that you see during the training process. To take that work forward, what we've done is the team has consistently worked on this piece since 2015. And in 2018 and 2019, we were able to put forth a bunch of new innovations. And that's what you see on this particular chart again. And as you can see, in 2018, we successfully showed, both in URIPS 2018 and URIPS 2019, we showed that we could train 8-bit models. That's what the green curve here is, shown here. We could train 8-bit models without losing any accuracy. And we also showed in 2019 and 2018 that we could do inference on a wide spectrum of deep learning models in either 2 bits or 4 bits without losing any significant accuracy. So what this really led us to believe since 2015 is that, similar to Moore's law of scaling, that has enabled the CMOS devices to increase in density and improve in power efficiency in each technology node, we can create an analogous roadmap for AI, and specifically for AI hardware, whereby we consistently figure out new ideas, new techniques by which we can scale the arithmetic precision needed for deep learning training, which is the green curve here, and deep learning inference, which is the blue curve here. And we are able to harness that low precision arithmetic to get increased power efficiency in these in AI hardware. So this is kind of a roadmap that we and IBM Research have put together. And we believe that we have a long way to go in terms of further reducing the precision. So our belief now is that in time, we'll be able to reduce the precision for training and inference by 2x every 3 years. That reduction in precision for training or inference can improve the energy efficiency of the hardware by at least 4x, if not 8x, for each jump of this precision roadmap. I'll talk a lot more about it throughout this talk in terms of being able to describe what are the key innovations that have allowed this to happen. But I just wanted to give you first a vision of how we see the space and how we believe we can help deep learning training and deep learning inference by building hardware and increasingly low precision arithmetic and while maintaining full model fidelity. So let me take to go into a little bit more detail into some of the key innovations that our teams have put together. I'll first focus on inference. I think the key thing with inference that we learned back in 2018 was that inference requires both weights and activations to be quantized to less than 4 bits. So today, inference is done with 8-bit arithmetic. 8 bits are used to represent both weights and activations. We realize that as you try to reduce the precision down, we have lots of challenges. And one of the biggest challenges is focused on how do we quantize activations. And one of the things we studied in 2017 and 2018 is if you take a function like ReLU, which is the activation function that's common to all CNNs, and you quantize it, because ReLU has an unbound range, essentially you can get a lot of, if you pick that full range, you can get a significant quantization error. On the other hand, you can take ReLU and you can clip it. You can say, hey, you know what? I don't want to go all the way to 80. I just have to support values up to 6. When you do that, your quantization error drops significantly. However, your clipping error increases because the network was expecting to produce activations at high values. So there's this delicate balance between quantization error and clipping error. And how do we get around that, right? Likewise, from a weights perspective, from a weight quantization perspective, the challenge always has been, you have the weights from a deep learning training process. How do we find the right quantization scale? How do you take that floating point weight distribution? How do you scale it in a way that is consistent with, how do you convert that into an integer quantized representation? And what is the right scale factor? Lots of papers have been published on this. And in fact, there's about almost to the extent of one paper a day coming out of the space right now. And a lot of these papers kind of use, at least the ones back in 2017 and 2018, focused on using the expected value of the weight distribution to capture the weight distribution. And that works reasonably well, but when you go to very low precision arithmetic, that results in significant errors. So our objective was to find a better scheme to be able to quantize weights. So that's what we did in this work, which was published at SysML in 2019. We focused on 3 key ideas here that allowed for the very first time activation quantization, weight quantization to work down to very low precision arithmetic. So to do that, we came up with a new technique called PACT. PACT stands for parameterized clipping activation. And the idea for PACT, and I'll share that in a slide or so, is instead of manually determining what the clipping value is, we let the network figure it out. We let the network learn what that clipping value is and automatically learn how to balance clipping error versus quantization error. From a weights perspective, we came up with a new technique called statistics-aware weight binning. And the key idea here is to figure out how you can exploit not just the expected value of the weight, but deeper weight statistics to be able to better capture the weight distribution. And finally, I think one of the key ideas we had was in a lot of these residual networks, gradient flow is very, very critical. So when you quantize the residual path, essentially you clip the gradient. So what you have to do is to make sure that you leave behind those shortcut paths and keep them in high precision arithmetic with the objective that you can enhance the gradient flow through that piece. And that becomes very critical towards preserving accuracy, especially as you reduce the weight and activation precision for all the other layers. I won't go into much detail into each of these topics, but I just wanted to introduce them, and many of these papers are published, so I'm presenting references as well. You're welcome to go back and look at if you're interested. The key idea for PAC, which was the activation quantization technique, was to figure out how the network can automatically learn the clipping value. So you have a function like ReLU, it's unbounded, you have to clip it. And instead of clipping it manually, make it a trainable parameter that is auto-tuned by backpropagation. So this is what we did. And so we came up with this idea where we initialized to a large value at the beginning, and we let the network figure it out. And essentially, it emulates ReLU in the beginning, but through the training process and through regularizers that are imposed on alpha, it goes, as you can see in this picture at the middle, at the bottom, the value of alpha decreases from a high value down to a very low value. And the network learns to live with this clipping because it has been trained with that clipping in mind. And as you can see in the picture on the right, if you were to manually pick the clipping value, you have a lot of dependency on the human itself to figure out what the right clipping level is and what is the impact of that on the accuracy. But PAC is phenomenal in that it is able to determine this value automatically and get to this minimum just by virtue of the fact that it's just another parameter that is trained and auto-tuned by backpropagation. So this is a new technique. Since our initial work on PAC, this technique has gotten a lot of excitement, and people have improved upon this technique as well. And a lot of newer techniques have come out that have overcome the challenges that we first had with this technique when we discovered it 2 years ago. Similarly, from a weight quantization perspective, we investigated multiple techniques. One of them is that we published called Statistics of Our Weight Binning. And the key idea here was to figure out exactly, instead of just using the expected value of the weight, we used the first and the second order moment to be able to directly predict or calculate the scaling factor. So we did this based on looking at different distributions of the weights. And we concluded that using those distributions, we concluded that this particular formula would be the right formula for computing the scale factor for weights. And basically using that particular formula, we can get the scale factor for weights and use it to do weight quantization. And finally, the key idea, the third key idea that we presented for inference was to focus on how do you minimize the gradient backpropagation that is needed for quantization of our training. And specifically here, the idea was, as I mentioned before, we focused on essentially looking at the shortcut residual paths, which are very, very critical in these deep networks for gradient propagation. But those particular residual paths only contribute to less than 1% of the total ops. So those layers are kept in high precision arithmetic, specifically 8 bits or 16 bits, while the rest of the network, which is 99% of the ops, are converted to 2 bits or 4 bits. So combination of 3 different techniques have been employed together, right? So the first is for activation quantization using PAC, weight quantization using the SOBI technique, and the full precision shortcut that preserves the gradient flow in these networks. I just wanted to give you a highlight in terms of what the key results were. So back in early 2019, and this pace moves really quickly, our techniques were the state of the art in the world. We were able to show that across a wide spectrum of different image processing models, we had no loss in accuracy for using 4 bits for inference. For 2-bit inference, we did have loss of accuracy, but it was in the order of about 3% or so. So this is a very powerful technique that for the very first time could result in models at 4 bits without losing any accuracy, any significant accuracy at all. I just wanted to, in the interest of time, jump to what I believe are the key challenges going forward in some of these quantization work, right? Specifically for inference. So I think where we are today with respect to the state of the art is for 2-bit inference on popular ImageNet models, we can get currently the best results show an accuracy gap of about 2.5%. And this is in spite of the fact there's been a lot of work, tremendous amount of work, focused on weight and activation quantization across the industry and across universities. But this gap still remains. So it's a very key area of research that I think would greatly benefit from new ideas and new thoughts. And I think those, even though popular ImageNet models work really well, down to 4 bits, I think quantizing mobile nets and smaller vision networks is becoming challenging. There's also not a huge body of work on object detection networks, things like semantic segmentation networks, things like mask-R CNN or YOLO V3 and SSD and things like that. This is a critical piece of work that needs to happen to be able to enable a future where all of the inference is done either in 4 bits or 2-bit arithmetic. And I think, finally, I think a lot of folks, both in the industry and academia, are very obsessed with ResNets. But I think a lot of the deployment models that we see in our cloud systems are largely focused on LSTM models and transformer models. So I think those kinds of models, the amount of work done on 4-bit quantization is very, very limited. So I think that's a very hot area for research, and I would strongly encourage students to look into those areas, because in many ways, those are the key problems that we in the industry face as we look to deploy these low precision arithmetic hardware in our cloud and edge systems. And finally, I think the key point to think about is focused on how do we combine quantization and sparsity. Both of them tend to reduce accuracy a little bit. So is it better to take quantization and not take sparsity, or do we combine dynamic sparsity with quantization? Those are all areas of research that I think need to happen over the next few years. So this covers my section that focus on inference, and I'll spend a little bit of time, maybe about 10 minutes or so, focusing on training. This space is extremely exciting because there's a lot of work that has happened from various groups, including us, that focuses on how do you improve the training system performance, which is a key problem that we have today, right? And one of the key pieces of work that we've done in this space that laid the foundation for this work is the 2018 NeurIPS publication we had focused on 8-bit training, which was the first demonstration of 8-bit training in the industry. So let me give you a little bit of a feel as to what the key challenges are, right? So today, all of the training happens either on FP32 arithmetic or FP16 arithmetic. So today, for example, the most aggressively scaled systems that are available focus on FP16 for data representations and FP32 for accumulations and weight updates. So as you can see in this chart, if you just take that system we have today and we simply change just the representations, you change all the weights and all the activations of the neural network to be 8 bits, you notice that there is a 2% loss in accuracy, which is significant. Likewise, instead of doing 32-bit accumulation, if we do 16-bit accumulation, we notice that, and keep everything else the same, we notice there is a 1% degradation in the accuracy of the model. And finally, today, all the systems we have focused on 32-bit master copy weights. And the key question here is, if you reduce it down to 16 bits, you get a significant accuracy degradation to 1.7%. And finally, when you combine these three, you get about a 3 to 5% accuracy loss. So this is telling us that prior to our work, doing 8-bit arithmetic, 8-bit multipliers, and 16-bit adders was not feasible. So the key piece of work we did that was published at NeurIPS focused on understanding this challenge and figuring out where the problems are coming from and proposing solutions at the intersection of hardware, software, and algorithms to be able to fix them. So let me try to first explain a couple of key innovations that came up, right? So I think the first part is the FP8 data representation. The right format is very critical. So depending on the format, you can actually lose significant accuracy. So that's one piece. The other piece we learned is that in the training process, it's really critical to make sure that the first layer, which is what's seeing the input, and the last layer, which is what is seeing the connected to the softmax layer, those are very critical layers. So, and those layers typically contribute to less than 1% of the total ops. So it's better to preserve them in FP16 arithmetic, right? And so coupled with this insight, we said, okay, we could do FP8, we could pick the right precision, which we at that time chose to be 152, And this essentially stands for 1 bit of sine, 5 bit of exponent, and 2 bits of anti-sine, right? So we conclude, this is the right, so we concluded at that time this could be the right format, and we could use it to be able to pick the right set of, the right format for quantizing all the weights and activations in these networks. The second key innovation that we showed was in accumulation. So as I mentioned before, all the accumulations today are done in 32-bit arithmetic. But what we realized is that what's happening is that the reason we needed 32-bit arithmetic was this phenomenon called swamping. And swamping is a challenge that happens with FP16 or any floating point arithmetic. And the key idea here is that when you add two numbers, if one number is much larger than the second, then by definition, you add those two numbers together, you are unable to preserve the fidelity of that accumulation. So what we said is, okay, so this happens because in deep learning, you're trying to compute long dot products. And those long dot products fundamentally have, you have accumulating a long sum, and then you add a running multiplier value, multiplicand value. So what we learned is there's a very easy way to solve this problem. So instead of doing a really long dot product as a running sum, we just divide the long dot product into smaller dot products, and each of those dot products could be computed. Now, each of them work on a smaller sum, but essentially, so don't have to worry about adding a large number to a small number. So fundamentally, we learned that FP16 accumulation can easily work if you just reverse, or if you just rethink the problem. If you just think about doing the accumulation in a different way, where instead of doing it in a linear way, you do it in a hierarchical way. And that really was a key idea that enables FP16 accumulation as opposed to FP32 accumulations. So based on all of that, we basically did a bunch of, back in 2018, we showed that across a bunch of vision networks, we could get extremely good accuracy, less than 0.5% loss in accuracy, using floating point 8 arithmetic. And this was the very first demonstration of floating point 8 arithmetic when applied to a wide spectrum of models, including ones as large as resonant 50. And again, the way this succeeded was because we combined a bunch of new ideas together. We combined the idea of doing the right FP8 formats, combined it with this hierarchical chunk-based accumulation idea. And we also had the concept of doing what is called stochastic weight updates. And you combine those three, we can enable 8-bit training for all of these different networks that you see here. I won't go into a lot of detail into this piece, but we also have worked with Professor Schanbach and his student Charbel at UIUC to understand how do we quantify this? So how do we quantify the idea of doing hierarchical accumulation? And we did a lot of work here that was published last year at ICLR. And the main insight here is that what we learned is what really impacts accumulation and how do we need to divide that accumulation into smaller accumulations is the concept of variance. And the idea is that we have to maintain the variance of the accumulated result. And so when we started looking at that, we said there's a relationship between the precision of accumulation, the accumulation length, and the hierarchical nature of the accumulation and the variance itself. This was work that was published, and there's a lot of math on this chart that obviously we won't have a lot of time to get into, but it really laid the foundation, a theoretical foundation, for being able to quantify this in a way that gives us confidence that, hey, we can do this hierarchical accumulation at 16-bit arithmetic, using 16-bit arithmetic, and still get extremely high accuracies for a variety of different models. I think this particular work also describes a lot of specific analysis that was done on a variety of networks, and we showed that our insights matched the results we can get on basically when we run these networks at different accumulation precisions. So I won't go into the details of all of this, but it's a very, very interesting piece of work that we did in collaboration with UIUC, and really helped us gain confidence in the idea that we can do these accumulations at low precision and still preserve accuracy. I wanted to spend maybe about 5 minutes talking about some of the recent innovations since Europe's 2018. So our work in Europe's 2018 was the first to show that you can do 8-bit training. But we quickly realized that that works really well for ResNet 50. If you look at things like MobileNet v2 or transformer models that are obviously widely used for NLP, you get a lot of accuracy degradation. So for example, in MobileNet v2, depending on the width multiplier, you can get a good 3 to 5% loss in accuracy. Similar things about the transformer. So what we decided is maybe instead of going lower in precision below 8-bit, let's first solve these issues. So this particular publication, Europe's in 2019, was focused on basically extending the 8-bit training work to a wide range of new networks beyond the ones we studied in Europe's 2018 work. So to do this, we basically came up with this concept of hybrid FP8 scheme. And the key idea here is the following. Instead of having just one 8-bit format, which is what we refer to as 152 in the previous publication, we have two different 8-bit formats, one with 4 bits of exponent and 3 bits of mantissa, and one with 5 bits of exponent and 2 bits of mantissa. And the key insight here is that in the forward path, for a lot of these networks, especially mobile nets and transformers, the precision matters a lot. So essentially, you need 3 bits of mantissa for the forward path. But the gradients, you need to have dynamic range. So you need a wider exponent. So the gradients are represented and the losses are represented in this 152 format. So this is what we refer to as a hybrid FP8 scheme, where we pick two different formats, basically what we call 143 with bias, and I'll talk about what bias is in a bit, for weights and activations, and 152 for gradients. And once we did that, we recognized that a lot of the fundamental issues associated with 8-bit training went away. And the insight again is that the forward path needs to be much more accurate than the backward path. And the gradients in the backward path are reasonably represented with this format, but the weights and activations in the forward path need a little bit more fidelity to be able to represent the range as well, to represent the values well, so that they can live with a smaller exponent, but a larger mantissa. So we did a lot of, this paper also describes a lot of the insight in terms of the analysis of why we came up with those ideas. And we had a lot of different tools we developed for this purpose. So on the top, we extended the work that you see that was focused on mismatch probability. And the idea here is the understanding that mismatch probability gives you a good way of studying what the right formats are for weights and activations. So we use the mismatch probability analysis technique to be able to study different formats for floating point formats, 8-bit floating point formats for weights and activations. And this showed us that for the forward path, the right format would focus on 143 format with the distribution that has a bias, which basically means that the entire distribution is skewed slightly backwards. We also did a lot of analysis back then, a year ago, that focused on how do you look at these deep learning models and how do you analyze how well things are going during the training. So this is an example of that work where we look at the loss surface. And as you can see here, 32-bit, the loss surfaces are great. When you start looking at the 152 floating point 8 format, the loss surfaces become jagged, which basically means you have the ability to be stuck in local minima. However, on the right side, if you pick the right formats, this looks a lot better than this. So essentially, you have a much higher chance of reaching the minima by using the 143 format for the forward path. A lot of these details are in the NeurIPS publication. So if you're interested, please do check it out and let us know if you have any questions. I also wanted to highlight a particularly important point, which focuses on what we call transposition inference, which is you train the model in 32 bits, but you want to be able to deploy it in FP8. So this paper also describes some of those key techniques that are needed to be able to do that piece of work. And specifically here, we did work on, I think the key insight here was when you train a model with one precision and you deploy it in a different precision, you need to update, in some cases, the weights, but in many cases, all you need to do is to update the batch norm statistics, because the batch norm statistics were developed for that particular precision and they need to be updated. So what we showed is that when you use the right 8-bit format and we update the batch norm statistics, you can get accuracies that are very close to the full precision accuracy. Again, this is not for training, this is for inference, where you train the model in 32 bits and you're just trying to deploy it on the new hardware and figuring out what are the right things you need to do to tweak that model to be able to deploy it in 8-bit arithmetic. This chart is kind of the money chart where we shows you all the results we've had across a wide spectrum of networks. So this one extended, this is the, again, the work that took a wide range of networks beyond just ImageNet. So we looked at transformer networks, we looked at various object detection networks, we looked at LSTM speech models that are deployed in IBM systems. And we showed that this FP8 training, and specifically the hybrid FP8 training, works really well across the entire spectrum of models that we studied back then. And we have since then significantly expanded this list beyond this as well. And we believe it's extremely robust from a training perspective to be able to support a wide spectrum of different kinds of networks. So it fully preserves accuracy, as you can see from this chart, for speech, image classification, object detection, language, and so on and so forth. So very, very significant piece of work that we were very excited about, where we were able to finally show that 8-bit training has become so robust that we can now use it widely to do training. And the key motivation, again, from an 8-bit training perspective, is if you build hardware with 8-bit training, with 8-bit support in it, and specifically the hybrid FP8 support, then you can build these systems so that have 4 times the training throughput of what you will get with today's 16-bit system. So very, very significant from a throughput perspective, and very, very excited about what this means for the future of training. This is just showing a couple of additional charts that focus on essentially a couple of these challenging models I talked about at the beginning, and we can see that even for mobile nets, there's no loss in accuracy anymore, and transformer models converge really well as well with this hybrid FP8 format. I just want to spend maybe 30 seconds talking about this concept of compression for deep learning training. So the key idea here is training is not done in isolation, right? So you have multiple accelerators working together on a large training job. And when you improve compute, like we showed with the previous set of charts, then you have to be able to improve the communication bottleneck. So we did a lot of work on the space back in 2018, and we have significantly expanded it beyond that since. And this is a key idea that we've proposed called ADACOM, which is a gradient compression idea, where essentially what you do is you take the gradients that are communicating between the learners, and we compress them through some form of lossy compression. And the idea there is that once you do that, the amount of data you're communicating between these different chips becomes a lot lower. So you're able to communicate much more efficiently. So you're able to stay focused on compute instead of waiting for the communication to complete between these different chips. We've shown a variety of different kinds of compression techniques, and other folks in the industry have also shown different techniques as well. I think in some cases, we can easily get 16x compression. In many cases, we can easily get up to 512x compression. So as you can imagine, in these kinds of systems now, if you get up more than 100x in compression, you're really at that point limited by compute again. So now you can focus on compute, and you can reduce the precision even further and improve the computational efficiency. So this is this delicate balance that one has to keep fighting between communication and computation. So I just wanted to highlight a couple of key points here. One is that in these systems, I think the 8-bit training problem is essentially a solved problem. So the next big step forward is 4-bit training. What kind of new ideas can we bring to bear to enable 4-bit training to work, or somewhere between 8-bit and 4-bit training? And there's a lot of work happening in RISE as well on this front in Celine's team. So I'm very excited about some of that work as well. The compression techniques I briefly touched upon, they need to work across the network spectrum. There's a lot of work that needs to happen to make sure that it works for a wide variety of different models. And finally, that you can actually combine low precision arithmetic and compression together to be able to guarantee that the accuracy is preserved, not just with low precision arithmetic and not just with compression, but we combine those two. I just wanted to spend a little bit of time to talk about the other part of my team, which is focused on architectural work. And as you can imagine, when you talk about low precision arithmetic, the only way you can exploit it is by building hardware that has those exact formats, rounding techniques, and accumulation techniques inside the hardware itself. So since 2016, our team in IBM has spent a lot of time building a lot of different flavors of AI hardware, and we've published a lot of this work as well. And I think when you build hardware like this, you have to ask a lot of questions. You have to ask about what is the right core. Is it a large core that like a TPU, or do you want to build multiple small cores like a GPU? What kind of floating point formats do you support? What kind of programmability is needed? What kind of flexibility is needed for future proofing? What is the right organization? What is the right architecture? What is the right microarchitecture? How do we most importantly, how do we keep the processing engines busy? And one of the key things that we've learned here, right, is that GPUs work really well, but their utilization is very low. It's typically in the range of 20% or so. So how do you build hardware that has very high utilization, typically in the 50 to 60% range, and how do we go forward from that? And obviously, a lot of this combines with circuit design and power performance optimizations. So if you want to get a flavor of some of that work, I would recommend that you look at the VLSI 2020 paper, where we presented work that was done on a second generation chip in 14 nanometers, where we talked about the architecture, the microarchitecture, and the circuit design innovations that need to come together to build a state-of-the-art, high-performance, high-power efficiency AI core. Broadly speaking, extending beyond that topic, I think we have in our teams in IBM, we have a really exciting research agenda that essentially combines all of these different topics, right? We have a really strong algorithms team that is coupled with our hardware team and with our software and compiler teams, right? So a lot of the low precision arithmetic work focuses and enables architectural optimizations that exploit this low precision arithmetic, coupled with circuit design techniques and things like that. And then we build software stacks, compiler optimizations that focus on extracting the maximum performance from this hardware. And that feeds back into it. So once we get a bunch of compiler optimizations in, we get an idea of the performance and we use it to build the next generation of hardware and so on and so forth. So a lot of exciting work that is happening at that intersection between algorithms, hardware design, and software compilers. It's a really tremendously exciting time to be in this AI hardware space. So if you guys are interested in any of these topics, I would encourage you to reach out to me, and I'm happy to talk you through the right people in our teams who are working on these topics that you can connect with. Some of the future areas for research from our perspective focuses on AutoML in terms of automatically looking at, this is actually an old chart, is kind of the current set of ideas focused on how do you automatically build low precision networks, and how do you build adversarial robustness into these low precision networks. One last point I want to make here is that to do all of this stuff is very hard for one company to do. So in 2019, IBM launched the AI Hardware Center. This was launched in early 2019, and this is, think of it as a collaborative, open ecosystem where we bring together companies and, in many cases, universities to build AI hardware and software together. So as of now, just within less than a year, we have had about 10 industry partners and university partners working together on various aspects of digital hardware, analog hardware, performance, compiler stacks, so on and so forth. IBM also has a very extensive program on what we call the AI Horizons Network. This is essentially a huge program that funds multiple universities across the country. Our current set of universities that we collaborate with and that we fund includes MIT, UIUC, University of Michigan, IIT Bombay, and so on and so forth. So really our objective is not just to do this work and enable our business units to succeed, but also to collaborate, to do this in a way that is collaborative and open so that we can best ideas from the best folks across industry and academia and put it all together to build leading edge AI systems. So I just want to close with this chart. And I hope I convinced you that the new Moore's law of scaling for AI is in fact precision. So I think we have in our team and in collaboration with multiple folks outside, we have driven a stream of successive innovations that have steadily reduced the precision needed for both training and inference. A lot of these innovations seemed difficult when they first came out, but by the time we really understood what was working and what was not, we started to enable this in our hardware as well. And it's driven by a deep insight into how deep learning models work, how neural networks work, how backpropagation works. And lots of new ideas have come in over the past 5 years to enable this very low precision roadmap. And obviously, there's a long ways to go as well for both training and inference to further reduce it all the way down. A number of these ideas are already in IBM products and have been adopted by the AI hardware industry for a variety of different application domains. So with that, I want to thank you all for listening. I'm sorry I went a little bit over what I should have, but thank you again.
No problem. Thank you. This is really impressive. You had this vision to publish, I think, the first fixed point inference work, and also the first 8-bit training work coming from the same team, and also continues push the boundary from both algorithm and hardware. So now let's open up for questions. So in case I saw some of you already type your question in the Q&A chat. In case you haven't got the chance, so you can do so, or you can raise your hand. I will unmute you and you can speak your question. So the first one, Haorang, would you like to speak your question? Let me unmute you.
Hi, can you hear me?
Yes.
Okay. So thanks for the exciting talk. And my question is about the bit precision for accumulator. So will the bit precision of operand and accumulator cope with each other? Maybe there are some sweet points or such relations are not fixed and affected by some hyperparameters like the trunk size you just mentioned.
That's a great point. So the bit precision of the operands, the bit precision of the accumulator, and the chunk size, they are all interrelated, right? So
Yes.
we've done a lot of studies on that work. And I think if you look at the ICLR paper, it kind of connects some of them.
Yes, actually, we noticed about that paper. Yeah, I think that provides a very good predictor for predicting the bit precision for accumulation.
Right.
In different cases, and we also curious about whether it can generalize to other models like LSTM models for language processing or the graph neural network for the graph processing.
Yeah, so I think we have extended it since then for LSTM models.
Yeah.
We have studied a lot of transformer models with that architecture. And partly that's because, we run a lot of, one of the things I did not mention is a lot of this work, right, happens because we have almost the extent of about hundreds of GPUs that are focused on running these various experiments all day long, right?
Yes.
So in many cases, we have studied this in a theoretical way, and CNNs is one example of it, LSTMs is the other example of it. But transformers, we just ran the network and confirmed that it worked, BERT models and transformers. So those are things we have confirmed on the network level. We haven't confirmed the theory on that particular piece. That will be a very good area to look into a little bit more in terms of understanding the theory of, because the distribution of your partial sums will impact your accumulation precision and what kind of chunk sizes you need and things like that. So that's a very good point. We haven't studied that for transformers. We know it works, but we haven't studied where it breaks. That could be a good area for looking into a little bit more to understand whether the analysis we did also applies to some of these other networks.
Okay, thank you.
Sure.
And next is Chao Jian. I think I already unmuted you.
Yes. So hello, Dr. Gopalakrishnan, and thank you for your exciting ideas. And I found the papers from the CSML last year, the accurate and efficient 2-bit quantized neural networks is very interesting, but I'm a little bit curious about the two methods you proposed for activation quantization and the weight quantization. And I think the method will be called PAC, AWA, right? And my question is that could we use the nullable method for quantizing activations to weight, or we use the statistic method for quantizing weight for activation? That means I think the method for activation is nullable, and the method for weight is statistics. Could the two methods be switched for each others? Yeah.
Very good question. Excellent question. I think the answer is you could use it. In fact, we have used it. We did study both techniques on both. The ones we published were the ones that worked, right? So I can say one thing for sure, that the pack technique, right, or in general, anything that is parameterized has lots of challenges as you go to 2 bits. And part of the reason for that is because you have to be able to accurately determine a bunch of hyperparameters, right? For each of the layers, you have to determine what the right decay rate is, what the right learning rate is, learning rate scaling factor is, what the right alpha value is. So those are very challenging. From that point of view, SOBI, which is much easier, you just get the distribution and you apply it, is much easier. So I can tell you one thing for sure, that LSTM models, both techniques work really well. So SOBI can be applied to activations and weights.
Okay.
We have obviously studied parameterized weight clipping. The problem again is is that the parameterized weight scale factors also work really well. But again, the challenge is not just that it has to work for ResNet 50, it has to work across a whole spectrum of networks, right? And that becomes challenging because you have to then, for each network, figure out the right hyperparameter. So I'm actually a big fan of the SAWB technique more than the PAC technique, because in general, that has pure parameters to worry about, and that you can use that. And we have confirmed that SAWB works for a variety of different networks as well. But for the CNNs, PACT is about 0.5% better than SAWB. So I think if you want to get state-of-the-art accuracies, you have to use PACT or one of PACT's follow-ons.
Okay, got it. Thank you.
Sure.
And next is Zhi. Zhi, I already unmute you.
Yes.
Yeah.
Thank you. Thank you for the talk. Very impressive. So my question here is, can the tricks of floating point training be applied to fixed point numbers? What would be the potential challenges?
Yes. So actually, it's very interesting you mentioned that, because back in 2018, when we published the floating point work, Intel published the fixed point work. At the same conference, 2018, UREPS, and our posters were right next to each other, right? And so we learned some few things in talking to them, right? So first is the following. One is that when they do fixed point quantization, I think one out of the 2 back-propagated tensors is kept in 16 or 32 bits. So I don't know if it was weight update or whether it was gradient backprop. One of them was kept in higher precision. So only 2 out of the 3 techniques could be enabled in 8 bits. The other one was kept in 16 bits. So that's okay, but that's a challenge they had. In general, what we have learned is that and this is not a universal statement, but it just comes from our experience, right? And I think one of the lessons that we have learned is the 8-bit techniques, 8-bit fixed point techniques, you can use it. It may even work for 1 or 2 networks, but when you start to go across the entire spectrum of models, talk about transformers and BERT and Roberta and all of those things, the 8-bit fixed point ideas, you need the scaling factor and all of those things. It becomes much more challenging. The floating point aid, you just get the tensor and you're ready to go, right? There's no additional scaling needed beyond the scales that we talked about in the loss. So it certainly is a lot less cumbersome. In our experience, we tried 8-bit fixed point and we tried 8-bit floating point. The 8-bit floating point work is universally scalable, applicable, but the 8-bit fixed point work required customizations for every different kind of layer, every different network required different scale factors and loss scaling and this and that. So our intuition tells us now that really for gradients, it's really only the dynamic range that matters. So fundamentally, sticking to floating point numbers is a better solution and much more widely applicable compared to fixed point numbers.
Okay, thank you. Thank you as a hardware guy. So I really appreciate your works. We benefit a lot from you. Thank you.
Thank you. Thank you for your kind words.
And then to stay on schedule, let's allow the last 2 questions. So Yonggang, could you speak out your question?
Yeah, could you hear me?
Yes.
Yes.
Yeah, hi, doctor. So thanks a lot for your great talk. My question is, could you switch to the slide that shows the energy savings of the 8-bit and even lower bit over the 32-bit ones. Yeah, this one. Yeah. Actually, at the first glance, I was quite confusing about it. Then I realized it's floating point, right?
Yeah, yes and no. I'll tell you why. Because we build hardware with both fixed point and floating point, right? So floating point floating point is what this one shows, but it's roughly the equivalent, because fixed point arithmetic also is roughly, to give you numbers,
Yeah.
in 7-nanometer technology, floating point 8 would give you something like 5 to 6 tops per watt, and FP8 will give you 5 to 6 tops per watt, and integer 8 would give you roughly 8 to 9 tops per watt. So it's not that different. It's roughly in the ballpark of factors of 30% or something. So 8-bit FP and int 8 are roughly the same energy efficiency, maybe 30% or so different. And the reason for that is because what happens is, in the integer case, in the floating point case, you're accumulating to FP16. In the integer case, you're accumulating to int 32. So the accumulator power starts to drop. Also, in the integer case, your multipliers are much bigger. In the floating point case, the multipliers are 3-bit multipliers, not the 8-bit multipliers. So you add all of that together, you end up in a situation where floating point 8 and integer 8 are within 20 to 30% of each other.
Okay, thank you. So did you compare the energy efficiency of the 8-bit floating point with the 8-point fixed point? So do you think which one is better in terms of energy efficiency? Because you have explained from the
8-bit fixed point is definitely.
Yeah.
Yeah, so 8-bit fixed point is definitely better. I think, as I said, it's roughly 9 tops per watt versus 5-6 tops per watt, or in that range. But obviously, the fixed point arithmetic is only working with basically the for inference, right? For going to do training, the fixed point arithmetic, as I mentioned in the previous question, was unstable.
Yeah.
Not on network. So we think that floating point 8 makes more sense because it allows us to do both training and inference in one piece of hardware. But there may be applications specifically focused on the edge, for example, that could benefit a lot more from just 8-bit fixed point if you don't need to do any retraining.
Yeah, okay. So, okay, thank you. Yeah.
I'm going to ask the last question, Kailash.
Sure.
So this is so since your 2015 work, there has been a lot of low precision or for inference and training. In terms of evaluation metric, I think earlier the community used flops, and later we kind of agreed that's not the right one. But then there are very few or open source evaluation platform for fixed point inference and training. So what would you recommend the community to adopt for fairly evaluate benefits in hardware?
So there are so many different layers, right? So even if you use 16-bit arithmetic in GPUs and customized hardware like we do, you get a factor of 4 in performance difference between the two, even with the same precision. And part of the reason for that is because in GPUs, they have different 16-bit formats. They support denormalized numbers. And in many cases, what we do, and wider accumulation widths, and GPU architecture, the microarchitecture is not optimized for AI, it's optimized for graphics, right? So I think really at the end of the day, what should matter is a metric like sustained performance, which is you have a given power envelope, let's say 100 watts or 75 watts or 300 watts, and you just basically at the end of the day, use it to compute the net images per second or epochs per second, epochs per hours, or whatever the case might be. That gives you a measure of the sustained performance. So sustained tops per watt should be what I think you need to go after. And that is a much more complicated metric because you have to run the whole network end to end, and you have to make sure that you get the full inference performance. You can talk about for CNNs, you can talk about it as images per second per watt. And for training, you can talk about it as epochs per watt or epochs per hour per watt, or whatever the case might be. Make sense?
that will rely on you already have the customized accelerator, right? I think your work, even since 2015, you have the FPGA evaluation reported, but that might not be practical for most of the algorithm team. So
that's true. That's very true, Celine. I think for us, I think that's easier. But I mean, and recently, all of we build chips, right? So this particular chart talks about all the different chips you've built, and many of them have been published. But I do agree, it's much harder to do that. My recommendation in that scenario would be to look at, I mean, to start with, right? I think when you talk about floating point or fixed point or precision optimizations, I think even peak tops per watt would be a starting metric, because how peak tops per watt gets compared versus how that gets exploited it depends on the architecture, right? So you could if you have figured out a 4-bit training system, then you can just look at the peak tops per floor and say, if you have the right architecture, then you can do X, right? So I think that would be the best way of comparing it, in my view. If you don't have access to the hardware itself or the design itself, the best way to do that would be just to talk about peak performance in terms of tops per watt.
Makes sense. Thanks a lot. Thank you very much, Kailash, for the inspiring talk. And let's stay on schedule. And thank you all very much for attending the talk. Yeah.